queues are not just algorithms that you study on computer science, they're practically everywhere. Whenever you make a request to a server, there are many chances that it's hitting first a queue. And in the real world, of course, whenever you go, for example, to the post office, you wait in line, or if you're in a restaurant. The reason that restaurants and post offices use a queue is because they want first that when the queue is empty, you serve people, but they are practically can understaff. And thus, they can serve more people than they can take in parallel. Because it wouldn't make sense to have so many post office clerks because, at some times you do have too many people that come to the post office, but at other times you have low number of people. So this allows not only post offices, but also computers and servers to a little bit be understaffed. Because if when we created our servers, we would create enough capacity to handle any load on our servers, in many cases, we wouldn't need a queue because whenever you make a request, you get a response because the server is available. But this is not the case. We can be busy at times, we are understaffed, and so we let the request just as people wait in queue. However, this is not saying that everything with queues is just fancy and dandy and great, because queues have their own problems. First, you need to build a queue or use some kind of a queue, and this might mean you maybe even using a new server. And if you use a new server, you need to handle the server. And now the question comes, what happens if this queue is full? Because if this queue is full, this means that you may need to block new incoming. So if you said that the limit of the queue is 1000, then what happens to the customer 1001 when he reaches this queue? This is specifically a case where you have the queue that is building up, specifically when there is a high load on your servers. So while queues help you, they also bug you because you can drop messages when these high peaks occur. Queues help to decouple systems, and thus they help the systems that call each other to be some kind of asynchronous, because when you hit a server, you can get an ACK immediately, and then you just wait for the message to process. After all, if you want to send an email, you don't really need to wait for the response. You can just get an ACK that the message would be handled, and it's now in the queue. However, when you use a queue, it's not without risks, because it can accumulate, so the request can accumulate on the queue. So basically this means that the queues on servers have practically two modes of operation. One mode, everything is fancy and dandy and great because messages come and your server handles them and everything is just great. The queue might build up a little, but not much. But then there comes like a peak, the Black Friday, and then in the peak your queues blow up and then you start dropping messages. So this is the problem. This is one of the main problems when you use a queue, because you move the abstraction of handling into the queue, but now you need to take care of it inside the queue. And this can happen not only in Black Fridays or when you have a major load. This can also happen when, for example, your service is down. So when your service is down, let's say your email server is down, and then it comes up, then it would only find that its queue has built up to an enormous amount of messages in it while it was down, and now it would try to catch up and there would be drop off. So it's not only for high stress, it's also for cases. This risk and this problem can also happen in cases when you have a slight shutdown of the service or a major GC or something like that. So you might think that if your system is asynchronous, then latency is less of a matter, because for an asynchronous system, you say, okay, I just give back an ACK, and then the client need to handle this ACK, and then it would get back the result. But this is not true, because also in asynchronous systems, usually what you have is the queue. And if your latency becomes too high, then the queue will build up. In addition, when dealing with queues, you will hear the concept of a DLQ. DLQ is an abbreviation for dead letter queue, which is simply another queue. So it's not something super fancy, just another queue which store messages which cannot be processed at the specific time. So if there is like a failure and then a retry and then a failure, the message will end up in a DLQ, and then you would need either an automatic process that would handle this DLQ, or you would simply handle them manually. In addition, when the queue builds up, you need to differ between some build-up that you could have expected. I mean, it's a different case if you have designed your queue to stop receiving messages after 10,000 messages than if there is a buildup of 30 messages, so it's a slight peak, and this is perfectly fine. But when your queue burst out because it reached the limit, this is the special case that we should handle specifically. Multi-tenancy. Many systems use the concept of multi-tenancy. This usually means that you have multiple tenants in your system. A tenant is like a customer that uses your system. I mean, like a major customer, consumer, that will have its own consumers. And if your system is a multi-tenant one, then you can have queue. Now, the question is whether your queue should be a specific queue for a specific tenant, or it should be a general queue for all tenants or for specific tenants specifically. The problem is even increased once what you see is that when your queue is out of bound from the limit that you have set it up, then multiple consumers would be affected. This can be an extreme case because a single consumer might send only one request per hour. However, this one request would fail because the queue is already full because of a different tenant. And basically what you do when you have multiple tenants is that you try to be somehow fair. For example, you set the limit on the rate for different customers. So you don't want one customer to bomb your queue and bomb your servers. You limit it to some number so that even if it reaches the number, it won't decapitate your queue, but the queue would still be available for other customers. So this is a usual solution. What you will see is that we don't have a silver bullet solution. I mean, we have queue, we have its problems, and then we need to handle them one by one. And for the multi-tenant problem, the way we handle it is by allowing or prohibiting each consumer from moving past a certain limit of the rate. So although we have a queue, we should simply handle it like just any other synchronous system. I mean, we have a queue, yes, it's helping us a little bit in decoupling systems, but we still need to limit the rate, yes, just like in synchronous system. It's not a silver bullet, as we said. Another measurement that you can take in order to provide yourself with the better ability to handle queues reaching their limit is simply by having dynamic scale. So in this case, what you do is that if you have like a spike or a peak, or you're starting up the servers, then you start more than the required amount of servers so that they would be able to handle dynamically the peak. And thus you are enabling your queues less to be bombed by messages for consumers because you dynamically scale up or down. So far we have discussed the two items. One is to be fair with regards to consumers. You limit the rate so that one consumer would not bomb the queue. And another one is by having your actual servers dynamically allocated. Another thing you can do with queues is that if you have slow requests and fast requests, I mean requests that take a long time to process and requests that take fast time to process, then you can defer them to two separate queues. This is what happens in many shopping centers. You have a queue for up to 10 items and you have a queue for longer items so that you can deliver more users. If you measure the amount of users that are going out, then all of them can go to the ones with the up to 10 items and you would handle them faster. There is no need for them to wait for the slow queue. Another thing is that although you may think that FIFO is fair, first in, first out, I mean the first message that came to the queue is the one that you should handle next, sometimes LIFO makes more sense, because if there is a message an hour ago, then due to FIFO you might be tempted to handle it. But if you use LIFO, then you handle more recent requests to your server. And in many times, the more recent requests are the ones which matter more because they just happened and not a year ago. Another thing that you can do in order to manage your queues, and as you already see, managing queues is not a really simple task. So there are many things. You need now to take care of the queue being spilled over. Another way to handle the spillover is that once you have an excess amount of traffic, you simply direct it into a separate queue. This is like increasing your queue size dynamically. And this separate queue, maybe it would handle them more slower, maybe it would direct them to different servers, and maybe it would have a different operation to them. Maybe it would do a faster operation, so maybe it won't return the most optimal result on this separate queue, but it would return a faster result, which is less quality, but it's better for the users than getting no result. Sometimes you need to take care of your old messages. So if your queue has spilled over and you find that you have messages, let's take it to the extreme, a week ago, maybe they are not important anymore. Maybe you can just drop them and delete the old messages or pass them to a different server that would handle them in a different way, because maybe you want to handle differently a request that came 2 weeks ago than request that came 1 second ago. Another thing that you should take into account is that if you have an unlimited amount of threads that handles request on your server, then your server might be throttled down. So maybe you want to reduce the number of threads in your server so that it won't reach the throttling down and would deal mainly with context switching and with GC. You want your server to actually handle the requests. Also, if you are really downstream, which means your server is really inside of the cloud of your service, then maybe you could want to send back pressure upward and to tell the external servers, hey, I'm really busy, so tell the users the system is a little more busy now, or it's taking a little bit more time, so users might send less requests. Or other systems, maybe the other systems are automatic and it's not really important to them that everything would be processed now. Maybe an hour is also okay. So you send like back pressure and you say, hey, I'm really busy. Could you please defer your request to a later time? You will find that many of these tricks are tricks that you could actually implement. I mean, not every request need to be handled directly. Some work can be deferred to a later stage. So to sum up, you have successfully changed your system from asynchronous to an asynchronous one, and you have introduced a queue. So now you may think that everything is great, but no. An asynchronous system is just an abstraction over a synchronous system because, I mean, the world is like that you made a request and you want a response. You don't really care that there is a queue and an overload on your servers for various reasons. Either there is a really high traffic or some of the servers failed, so the other servers gets more traffic rate, or you have just restarted, or you have too many threads, so your servers are dealing mainly with context switching. So all these can cause spikes in the queue and you need to handle them. And we said that we can differ between slow queues and fast queues, or dynamically resize our queues, or scale automatically our servers. Use LIFO instead of FIFO because the more recent messages are more important, or direct the dead letter queue, direct messages to the dead letter queue as called DLQ, which is just another queue. Yeah, it's nothing so special, just another queue that you handle it separately. And all these mechanisms are mechanisms that you should at least be aware of when you design a system that has a queue. So it was great talking to you about queues, and I will see you next time in the next interesting episode.